Now we're going to do some I had before. And I'm going to ask you a question. To test if age and income are related, research collected these using my 0.05 like table and our degrees of freedom. We're going to calculate degrees. So from that, we will take our decision rule. And for that, we have our own special R table. There are tables for everything. So using our alpha of point, and for that, we have our own special R table. There are tables for everything. So the incomes. Using alpha 0.05, are they related? It is greater than 0.6. So I don't want to go through it again, but here's everything that we did. And this is a process that we worked through in order to come with that hypothesis, 0.62. We're going to reject the null hypothesis. Next, we will calculate the test statistic. Now, in my last example, I've already done this exact thing, so I don't want to go through it again. But here's everything that we did. And this is a process that we worked through in order to come up with our R of 0 back to the last buffer with the null, and our reject the null hypothesis. Therefore, concluding that there is a relationship between age and yearly income.
In hypothesis testing for a population correlation, in hypothesis testing for a population correlation coefficient, rho, we use a sample of ordered pairs, like these, to calculate a standardized test statistic and reject or fail to reject a null hypothesis, depending on whether that test statistic falls in a rejection region. And this test tells us whether the correlation between two variables is significant. The usual pairing of hypotheses are listed here, with the null hypothesis representing no significant correlation. And as with other hypothesis tests, they can be one or two-tailed tests. When testing for population correlation coefficient, we use a t-test. And the formula for calculating the standardized test statistic is t equals r divided by the square root. Calculating the standardized test statistic is t equals r divided by the square root of 1 minus r squared over n minus 2. In this formula, t is the standardized test statistic, r is the sample correlation coefficient, which is calculated using this formula from a data set of ordered pairs, and n is the number of ordered pairs. And the degrees of freedom is equal to n minus 2. All right, let's go through a full example step by step. Here is a data set for video views on my YouTube channel and subscribers gained for 16 randomly selected days over the past year, with views being the x or independent variable and subscribers gained being the y or dependent variable. The r value or sample correlation coefficient equals 0.9 variable. The r value or sample correlation coefficient equals 0.9067 at a level of significance of alpha equals 0.05. Test the significance of this correlation coefficient. Step 1 is to identify the null and alternative hypotheses. The null hypothesis h sub 0 is rho equals 0, that there is no significant correlation. And the alternative hypothesis is then rho does not equal 0. Step 2 is to identify the level of significance, which was given alpha equals 0.05. Step 3 is to identify the degrees of freedom, which is n minus 2. So
two-tailed.
Because the alternative hypothesis contains the does not equals inequality, this will be a two-tailed test. Step 5 is to determine the critical values. Graphically, this looks like this, with our critical values, negative T naught and positive T naught here, and both of these shaded areas in the tails being rejection regions. Since the level of significance is alpha equals 0.05, and this is a two-tailed test, each of these rejection regions will be 1/2 of alpha, which is 0.025. And in the t distribution table, that value is negative 2.
One 761. What? Oh, 2.145.
And positive 2.145. So those are our critical values. Step 6 is to identify the rejection region. And our rejection regions is any standardized test statistic value that falls in the shaded area, or the value of the standardized test statistic. And in our example, we have t. Equals 0.9067 divided by standardized test statistic is greater than positive T naught, the critical value. 2. Step 8 is to make a decision to reject or fail to reject the null hypothesis. On our graph, you can see that the standardized test statistic does fall in the rejection region to the right, as T, the standardized test statistic, is greater than positive T naught, the critical value. So in this case, we would reject. All right, my friends, that is the base.
What is this doing? The hell? The hell? The hell? What is going on here?
A correlation of a sample is So here we've got a question.
Okay, in this question.
Well, as noted earlier, if the central correlation R is close to 1 or negative 1, we know that that part follow the same idea. Okay, so therefore the see the
Okay, so what we did last lesson is we learned about patterns and things. That's how humans work. We see things and we want to be able to draw conclusions from them. So somebody, back of your booklet, usually when we have, and what can we say about how values are? The 0 point. A gradient. What did tell you about the gradient when you did your calculation? The b was the bit that goes to the x, and if you put it in the a plus bx form, the value of b tells you the gradient, and the value of a tells you the y-intercept, which we'll be able to use in this application. So we now want to say to ourselves, okay, well, what about if things are so up on my calculator as being correlated? How confident can I be that there is actually a correlation between these two things? So I'm going to use an example here from a spreadsheet that has randomly generated math marks for students, and it has separately generated random English marks for students. So this first one that I've done here, these are two separate experiments. This first one, where there are 10 students, I randomly gave them these English marks here, and randomly gave them these maths marks here. Now, if these numbers have been given out completely randomly, there is no real life relationship between the English marks and the maths marks. There's no relationship because they were assigned randomly. And if something has been assigned randomly, we shouldn't then be thinking to ourselves that there is a correlation between them. So what you notice here is that the observed PMCC, the value of R, between maths and English in this first set of data is 0.219. So you would do this calculation and you would think that there is a relationship between these random numbers when we know that there is no relationship between these numbers because they are completely randomly artificially generated. So the true PMCC between maths and English is actually 0. There should not be a statistical relationship between these two things because if there was no that rho is going to be greater than 0. The sum.
Let's carry out a hypothesis test on whether there is a positive correlation.
Sample size, how many people did we take in that sample previously? Remember the observed PMCC, which is positive correlation, is independent.
Third eyes. We test 62.9, 11.24, 8.8, 9.65, 60.44, 9.3. Shit.
Higher population base. Our R is greater. And
Sample size 10, the sample size 8.
the observed
let 8 with 10% with 10% significance level 8, and then we find our 0.10 here, which is 1.395.
Well, but you don't look at the Spearman coefficient because that's for something that comes much later on. You look at the product moment correlation coefficient or the product moment coefficient, and you look at the sample level, and then you look at the significance level. So my sample level is 10. This is a different color, so I'm not looking at it obviously. My operator, that's my sample that we get. So to do here, so option between these two things.
R is 1.218899. Oh shit, why don't we just, god damn it. So people rejection trả bảng student với degree bằng 8, confidence level alpha bằng 0.10. That would give us 1.397. 1.9397. But it's smaller. Wait, no, it's smaller. So there's no way we're not gonna.
Is the PMC normally? So I'm going to say that 0.219 is less than 0.4428. So
No, if not enough evidence. Let's go.
down here, if you just take the negative value from the table, if you're looking at the
Table. Wait, let me see. 4428, right? Yes, that's right. Let's go. I understand the correlation between the two now. 30 observations of the masses for two reactants experiment is he calculate the product moment correlation coefficient of rho equals is negative not 45 negative 0.45. There's no correlation. Scientists claim. But the sample size is huge. Huge. You know? It is huge. 10% significance. Yes. It's no larger than 30. Then we can safely assume that. Let me see. This is negative 0.45, right? There's 10% significance is gonna be this. 10% with two-tailed tests. So it's gonna be 0.05, 1.645, 1.645. Then it is just literally a normal distribution at this point. equal 5. Then we're gonna calculate 0.645 times square root of 30, 28. Wait, it's just 28, right? Just 28. So our rejection is not that is 1.701. That divided by 0 minus 145 square 2. So there is a correlation. There is a correlation.
Every, okay? Must be 0.3061. But remember, the value that we've got is minus 0.45, so we're going to have a look at negative 0. So we'll do 0.3. Because the scientist believes that there is no correlation. So is the scientist right wrong? Okay, so this is actually maths are correlated, and the scientist. So this to the other end, the critical reason is theta. So we've got, so I'm going to do one more.
Wait, that is supposed to be. Oh, sample size. Damn. The test. If it's really 1.701, okay? 0.61 times square root of 80 to the 8 minus square root minus 51. It is true. That is because sample size, the critical value for R is this. Is correspond to the critical value for standardized critical value at 28 degrees. Makes sense?
So let's now just have to type things and have this. So we've got
Okay, G squared.
So in most statistics classes, students are supposed to learn a dozen or so statistical tests. And a really great students are supposed to learn a dozen or so statistical tests. And a really great question I get from my students every semester is, how do I know which tests I'm supposed to use? And that's a great question considering there's like a dozen of them. And if you just learn all of the different statistical tests, then you end up leaving a statistics class thinking, I mean, I know all these tests, but I just don't know which one to use and when. So this lecture is going to be dedicated to
Let's go!
types of statistics tests, specifically the ones that are typically involved in undergraduate level statistics classes, and when to use them.
What
So
the?
I'm going to first run through all the different tests that we'll be covering throughout this course, and then I'm going to analyze when to use which one. So there are one sample z-test for the mean, one sample t-test for the mean, one sample z-test for proportions, one sample t-test for proportions, two independent sample tests for the mean, two independent sample tests for proportions, max or paired sample tests, chi-square tests, regression tests, and one-way ANOVA tests.
Oh, what the hell? Wait, hold up.
And it can kind of be overwhelming. And then I will go different types and when. So this lecture is going to be dedicated to introducing the different types of statistics tests, specifically the ones that are typically involved in undergraduate level statistics classes, and when to use them. So I'm going to first run through all the different tests that we'll be covering throughout this course, and then I'm going to analyze when to use which one. So there are one sample z-test for the mean,
One sample z-test for the mean, one sample z-test for the mean. Two.
one sample t-test for the mean,
One sample t-test for the mean. I think it's when the sample size is small, we use t-test, right?
one sample z-test for proportions,
What? One sample z-test for proportions.
one sample t-test for proportions,
What the? The same.
two independent sample tests for the mean,
Two independent sample tests for the mean. What? Two independent sample tests for the mean.
two independent sample tests for proportions,
What? There's independent sample test for proportion.
matched or paired sample tests,
Pair sample test.
chi-square test,
Chi-square test. Wait, I have to send this video to my friends.
regression test, and one-way or paired sample tests, chi-square test, regression test.
Regression test, we just learned that really. We use T's table for that, right? Actually, T table when n is larger than 30 is exactly the same as normal distribution, the Z table.
And one-way ANOVA test.
One-way ANOVA test. ANOVA is variance, something variance? I forgot. Analysis of variance. ANOVA test. One-way ANOVA test.
That's a huge list
Yes.
of tests. And it can kind of be overwhelming. And I understand that. It took me a while to be able to understand which one to use and when. So in order to do that, I'm going to break down all these different tests, explain what they are, what their purposes are, is very similar. Let's talk about the chi-square test. The chi-square test is very similar. The chi-square test determines if there is a relationship with two variables that are qualitative. So in this case, I'm not going up to you and I'm not going to ask you quantitative questions. I'm actually going to ask you qualitative questions. So in this case, I might ask you, let me see if I can get this right. There we go. Yeah, so are you male or are you female? But I'm going to ask you two questions. I'm going to ask you what's your gender, but I might also ask you, let's say, are you blonde or not blonde? And I want to determine, is there a relationship between your gender and your hair color? Now, it's really hard to determine if there's a relationship because those are quantitative. You can't measure them on a graph. You can't plot points because these variables are binary. There are only two options. And so in this case, maybe we notice that there are, 100 male blondes, but only two males that are not blonde, and 3 females that are blonde, and 250 females that are not blonde. In this example, we notice that if you're male, you're probably going to be a blonde. And if you're female, you're probably going to be not blonde. There's sort of a relationship here. There's a correlation between these two variables. But it's hard to see there because we can't really graph it. There's no way to graph this. And so the chi-square test can solve this problem by allowing us to determine whether or not two qualitative variables are different from each other. Now, last but not least, we have...
Are you serious?
And that should hopefully clarify when to use which test. So let's start with the first category of tests. There are two tests in this category. This is the one sample Z test for the mean. and there is the one sample t-test. That's not how you spell test. For the mean. I'm going to break down the differences in a second here, but let me first address what this does. Suppose Apple claims that the average age of their user was like 45. Now, you and I both know that's not correct. So suppose we gather like a sample of like 1,000 Apple users and we find the average age. We have this average. I would want to clarify that we are calculating a mean here, and we're trying to compare that mean to what the scientific community believes in. So the scientific community, or I guess in this case Apple, believes that the average is 45. And we're trying to prove them wrong. We're trying to say, no, you say it's 45. I don't think it's 45. I actually think it's not 45. I think it might be around 20 something. Right? So you gather a large sample, you calculate the average, you notice the average is different than 45. And then these tests will allow you to determine if the difference between the averages, the average that you calculate with your sample, and Apple's claim, which is 45, these two tests will determine whether or not those two numbers are different from each other. Now, what's the difference between a z-test and a t-test? It's a great question. Pretty much nothing. So let me explain what I mean by that. First off, z-tests in general are terrible. They suck. They make the math a little bit easier, but no one should ever use a z-test. If you ever see z-tests in general, just avoid them like the plague because they make assumptions that should never be made in the first place. Typically, t-tests are way better. If I ever read a research paper that involves any statistics test, I will never see a z-test. And if I do, I'm going to start questioning the authority of what the paper is trying to say. So we're going to talk about this later on, but just for now, just understand that the one sample t-test for the mean is the purpose of that is to determine whether your sample average is statistically significant than what everyone thinks the average is. Now let's move on to the next category. The next category is very similar. It's the one sample z-test for, in this case, not the mean, but for a proportion. Now, what's the difference between a mean and a proportion? Well, a proportion is meant for rather qualitative variables. So, for example, I'm interested in maybe, are you a Republican or are you not a Republican? That kind of question is a qualitative question. And if I gather a huge sample, I can't really compute an average. Like, I would compute a proportion of Republicans. So, for example, if I gathered 1,000 people, I would say that the average is like Republican. Gathered 1,000 people, I wouldn't say that the average is like Republican. You can't really compute average if the responses are all qualitative. You have Republicans and not Republicans. Same thing with gender. If you gather a huge group of people and you want to know information about that group of people in terms of their gender, you have male and female, right? And the idea is you can't really calculate the average. You can't add up all the numbers and divide by the total number of numbers because the responses aren't numbers; they're qualitative responses. And so you can make it quantitative by calculating a proportion. So you might say, okay, well, 50% of the sample was male, or 51% of the sample was male, or you might say 70% of the sample was not Republican. And so now you have something to work with. And so these type of tests are more for qualitative variables. And the same principle applies. Let's say, for example, in the 2016 election, there were all of these claims that Hillary Clinton was going to win the election. And let's say people were saying that she was going to win, and people were certain that she was going to win by like, I don't know, it was like 50 electoral votes or something like that. Or that 65% of the people were going to vote for Hillary Clinton. Well, that wasn't the case, was it? Those proportions were incorrect. Those polls, in a sense, were incorrect, or the way they conducted their polling was poor, in a sense. It wasn't representative of the actual population. And so the idea is if someone comes out and says, no, I disagree with this claim about the proportion of people who are going to vote for Hillary Clinton. I have a different proportion. I think it's actually 45%. Now, are those two proportions different from each other? That's what these tests measure. These tests measure is your proportion of your sample, your one sample, different from what everyone believes the proportion is. Let me give you one more example. 75% of the people claim to be Christian, in the U.S. at least, in the U.S. What might be interesting is to say, I don't think it's 75%, I think it's a different percentage. So you gather a group of like 1,000 people, you calculate what proportion of that sample is Christian. You find it's 60%. Now the next question is 60% different from 75%? Or should I say, is it different enough to say, yeah, it's not 75%, it's 60%? And that's what these tests can do. But once again, what's the difference between a z-test and a t-test? Well, I'll tell you. it's sloppiness. If you use this, then you're sloppy. I know it sounds crazy, but that's actually legit. If you use a z-test ever, I'm baffled why you would ever use something like that. So far we've gone over 4 different tests, and these are all with one sample. But let's talk about what you do with multiple samples, and this is where things get kind of interesting. So first, let's talk about the 2 independent sample tests for the mean. So I'm going to write that down. The 2 sample independent tests are the result, and the other group not so much. The control group, no one's getting cured, right? You might notice that, hey, my treatment does something here, and it's statistically significant. That's independent test. For the mean. So this is really useful if you're conducting an experiment. Whenever you're conducting an experiment, you typically will have a control group and a treatment group. You will have 2 samples. And you want to know, are the results of these samples statistically significant? And so you want to measure the mean of this group, mean 1, and the mean of this group, mean 2. And the question is, are these 2 averages different from each other? Different enough to suggest that whatever the treatment was, it made a difference. So for example, suppose you found a cure to cancer, and you notice that the results of one group, all these people are getting cured, and the other group, not so much. The control group, no one's getting cured, right? You might notice that, hey, my treatment does something here, and it's statistically significant. That's the kind of thing that we're dealing with when we talk about 2 sample tests in general. Now, this is a 2 sample test for the mean. So cancer might only work for proportions, like we would say, well, 50% of the people here were cured, and the other 50% were not. That's more proportion stuff. I might be more interested in, let's say, how much cholesterol is in.
Which we're going to use. In this video, we're going to talk about the chi-square test, specifically how to use a chi-square distribution to perform a goodness of fit test. So let's use this example problem. The reason we do the value of R is greater. All in the left, first of all, well, testing linear. The school principal would like to know which days of the week students are most likely to be absent. The principal expects that students will be absent equally during the 5-day school week. The principal selects a random sample of 100 teachers, asking them which day of the week they have the highest number of student absences. The observed and expected results are shown in the table below. Based on these results, do the days for the highest number of absences occur with equal frequencies? What would you say? Use the 5% significance level to find out the answers. Now, the first thing we need to do is determine the null hypothesis and the alternative hypothesis. So for this problem, the null hypothesis is that the absent days occur with equal frequencies. That is, they fit a uniform distribution. The alternative hypothesis is that the absent days do not occur with equal frequencies, a uniform. This value here is not a symmetrical distribution. As you can see, it's skewed. This value here is known as the critical value, or rather the critical chi-square value. It separates the rejection region from the do not reject region. So this is the region we're going to reject the null hypothesis. Now let's begin by using the chi-square distribution table. our critical chi-square value square. Able to get our critical chi-square value. First thing we need to do is determine the number of degrees of freedom, which is equal to n minus 1. N is the number of categories our data is placed in. So the categories are the days of the week, which we're using 5 days of the week. So n is 5. 5 minus 1 is 4. So we have 4 degrees of freedom. Tell test is up, which is 0.05. So using this column, and we have 4 degrees of freedom, so using this row, we can see that our critical value is 9.49. So let's place our critical value that we're going to use is it's going to be sigma, which represents the sum of the difference between is we need to get our calculated chi-square value, and the formula that we're going to use is this formula. It's going to be sigma, which represents the sum of the difference between the observed values and the expected values squared, divided by the expected values. And we can find this in a table. The first row contains the observed values, and the second one contains the expected values, which have equal frequency. We're going to get our calculated chi-square value. Now, the goodness of fit test is a right set test. And so I'm going to draw a graph. Now, the chi-square, let me say that again. The chi-square distribution, the answer. And so we use this example problem. Basic hypothesis.
The average cholesterol in each group after giving a certain medication. And I noticed that the average cholesterol in the treatment group was, let's talk about the, yeah, so are you male or are you female? But I'm going to ask you two questions. I'm going to ask you.
Now, let's begin by using the chi-square distribution table to get our critical chi-square value. So the first thing we need to do is determine the number of degrees of freedom, which is equal to n minus 1. N is the number of categories our data is placed in. So the categories are the days of the week, which we're using 5 days of the week, square distribution table. And in the first column, we have the degrees of freedom. In the first row, we have the area to the right of the critical value. Welcome to this lecture and discuss how to choose the most appropriate statistical test for our study. Welcome to this lecture and discuss. Now both noun and paraphrasing. Finally, there are look at tests.